Newton's third law of motion. When two bodies interact, the forces they exert on each other are equal and opposite. That is Newton's third law. Okay, so what we can say is if body A exerts a force on body B exerts an equal and oppositely directed force on body A. So let's say we have two bodies. Okay, let's say we have two bodies. Let's say we have to consider some two marbles or something like that, or two balls. Let's say so we have one ball here and we have another ball there. It doesn't need to be identical. They can be different shapes, different sizes, or maybe two different objects. It doesn't matter. Okay, so okay, so what we have to do is, now you can see between any two bodies there is a gravitational force of attraction. Okay, so there will be a gravitational force of attraction on this body this way, exerted by this body. Okay, so if you take this body, the arrow I am drawing here is the gravitational force exerted by this body, exerted on this body by this body. Okay, so I will write, okay, so let's call this A, and maybe we can call this other one B. Okay, so this is the force exerted by B on A, sorry, exerted by A on B. I'll use this color. So force exerted by A on B, and here we have the force exerted by B on A. Okay, force exerted by B on A. All right, so here we have this. So this is the force. This is the force exerted by B, A on B. This is the force exerted by B on A. So this is object A, this is object B. Now these are both gravitational forces. Now if you take the gravitational force exerted on the earth by the sun, okay, so if you consider this to be the earth, this to be the sun, the gravitational force exerted by the sun on the earth is this one. The gravitational force exerted by the earth on the sun is this one. So this is a Newton's third law pair. Okay, so what Newton's third law states is that if body A exerts a force on body B exerts an equal and oppositely directed force on body A. And there are about 6 criteria for a pair of forces to be Newton's third law pairs. I think that is here in this book. Let's see, look and hope the page is there. Okay, for a pair of forces to be Newton's third law pairs, there are 6 criteria, and not all criteria are given in any book. I'll tell you what those criteria are, but actually this one may give you about maybe three criteria. Okay, but I think it was in this page, so that page is missing. Okay, anyway, I will tell you what the criteria are. Okay, so the two forces have to be the same type. The two forces have to be the same type. They have to act on different objects, and they should be the same size. Okay, I'll actually write it here. Okay, so we'll write it here. So for a pair of forces to be Newton's third law pairs, there are about 6 criteria. A pair of forces to be Newton's third law pairs. There are some criteria. Okay, so about 6 are there, but even with 4 or 5, you can figure it out. Okay, the first one is they should act on the same different bodies. Act on different bodies. Okay, act on different bodies. Okay, then also they should be the same type, size, same line of action, direction. Okay, so the two forces should act in opposite directions. And the last one is act for the same time. So they should be same time. So you can see here, you look at the shoe, like that impulse force I gave you. Do you remember that example of the impulse? When the bat hits the ball, the time that the ball is in contact with the bat is the same time that the bat is in contact with the ball. So the bat exerts an impact force on the ball, and the ball exerts an equal and oppositely directed impact force or contact force on the bat. So the forces they exert on each other are the same type. You get it? So they are the same type. Now even here, this is also Newton's third law pair. When the boy kicks the ball, the contact force exerted. Okay, first we'll examine each one of these. Okay, so you can see here, this is a Newton's third law pair. How do we identify whether it's a Newton's third law pair? Is if it meets these 6 criteria. The first thing is the two forces have to act on different bodies. You can see this is the force exerted by the shoe on the ball. So this force is acting on the ball, and this force this way is the force exerted by the ball on the shoe. So they act on different bodies, one acting on the ball, the other acting on the shoe. Then they have to be the same type. Both are normal contact forces. Another name for normal contact force is normal reaction force or reaction force or contact force. Okay, so both are the same type of forces, and they are the same size. Okay, so they will be the same size. The length of the arrow represents the size of the force.
So can't the forces be different?
No, if it's a Newton's third law pair, they should be the same types of forces. They can't be different types. They have to be the same type.
No,
okay.
No, size.
Yeah, they have to be the same size. So I told you earlier, all these criteria have to be met for them to be a Newton's third law pair. All 6. Yeah. Okay. So same type, same size, same line of action. Okay. So if you draw a line passing through this arrow, along this arrow, it also passes through this other arrow. So that indicates they have the same line of action and act in opposite directions. One is to the left, the other is to the right. Okay. So this is these are contact forces. So act for the same time. So that is the time in contact with which the ball is with the shoe or shoe is with the ball. Okay. Now the same thing we can apply for this also. Okay. So here you have 2 objects. Maybe one may be a pen and the other may be a book. Okay, so I model them as a particle, like using a circle like this. Okay, so if you use this one, then check this criteria. Act on different bodies. One force acts on one body, the other force acts on the other body. Then same time, same type. Both are gravitational forces of attraction. Same size. Both are the same size. Okay. Then so this weight is actually mg. This is the weight force, W equals mg. So each one depends on the gravitational field strength of the other. So if you consider, now it doesn't matter if it's a small object or a large object, both objects exert gravitational forces on each other. But this is prominent when they are massive bodies like the sun and the earth, or the earth and the moon, or earth and an artificial satellite. Okay, so if you take this to be the sun and this to be the earth, then this will be one weight force, this is the other weight force. So both will be the same in size. Okay, the size of the forces are the same. Same line of action. Now if I draw a line passing through this arrow, it will also pass through this other arrow. So both arrows are in the same imaginary line, or we can say the same line of action. Act in opposite directions. One is to the left, other is to the right. Act for the same time. They also act for the same time. Okay, so these are the 6 criteria that you should know in order to identify whether a pair of forces are a Newton's third law pair. Now, there can be other forces very similar to this, which have the same size, same line of action, which act in opposite directions, but they may not act on different bodies. So the reason I wrote, and they may not be the same type. The reason I wrote this first is because of that. Okay, so same different bodies, same type. Okay. So this, you can use this to identify whether it is a Newton's third law pair. I'll give you one example where a lot of students confuse. And there are also past paper questions which are related to what I'm going to show you now. Let's say there is a book on the table. We have a book on a table. Let's say this is the table. And let's say this is the book. Brown. Oh, it's brown. Okay, so let's say this is the book. It's on the table. Okay, it's not floating. Okay, it's try to draw it the best I can. Okay, so the book is on the table. All right, now if you draw a free body force diagram for the book, then you have to draw only the forces acting on the book. Okay, so the forces acting, and I will first draw the free body force diagram for the book. Free body force diagram, FBD or FBFD for the book. There, what are the forces acting on the book? One is the weight.
Yes, sir.
Weight. Okay, this is exerted by the earth on the book. Okay, and the other is the normal reaction force or normal contact force or normal reaction force exerted by the table on the book. So where the table is in contact with the book, there is a contact force or normal reaction force also. So it has different names. Okay, normal contact force, normal reaction force, contact force, all mean the same thing. Reaction force. Okay, so let's call that R. So these are the only two forces acting on the book. Now this force is equal in magnitude to this one. That's why the book is in equilibrium. Okay, now if you draw the free body force diagram for the table, okay, I will draw the table here smaller in size. Okay, just zoom, diminish the size of the table. Okay, so I will draw it small so that it's easy, I can manage it in this space. Okay, now the forces acting on the table are the reaction force exerted by the book on the table. Okay, because the book is in contact with the table. So if in any way, if two objects are in contact, then one exerts a contact force on the other and the other exerts a contact force on the other one. So both exert contact forces on each other. Then also you have a weight force acting. Weight force is the force due to the gravitational field. If this is on the earth, then that is due to the earth's gravitational field. So there is a weight force exerted on the table by the earth. Now let's check. Okay, first now we will draw this. Now usually the question is like this. In the past papers, they ask you a question like this where you have a book on a table and they draw this one, which is the weight. I will use the brown color so that it's easier. Okay. So what they do is, okay, so this weight force is drawn like that. And they also draw this reaction force. Okay, so the reaction force is like this. Okay, now what they will ask you is state why it is equal, why they are equal, and they have given you some choices. Okay, this was a past paper question and certain students thought it was because of Newton's third law. Now it is not equal because of Newton's third law, because if it's Newton's third law, then it has to meet this criteria. Okay, like I said, these are the two most important, because the others may be the same in most of the questions, but the first two are the most important. Okay, so let's apply this for this example. Okay, and we'll check whether R is equal to W because of Newton's third law. Now if it's a Newton's third law pair, the first thing is act on different bodies. Now are these two forces acting on different bodies?
No.
No, for the book, if you consider the book, both forces are acting on the book. So clearly it's not a Newton's third law pair. And also, are they the same type? Is R the same as W. R is the normal contact force. W is the weight of the book. So there are different types of forces. Okay. So I'll write same type. Okay, then let's check the other criteria. I think other criteria are okay. All right. So it has to meet all the criteria, not just some. So same size. Yeah, they are the same size. That's why the book is in equilibrium. If they are not the same size, then the book will not be in equilibrium. It will move. So here for the book, the resultant force is 0. Okay. For the table also, the resultant force is something I forgot here. There is also a reaction force over here, exerted by the legs of the table. The flow exerts a reaction force on the table, R1, R2. If forgot that. Okay. So the table is in equilibrium also. The resultant force on the table is 0. Okay. Because the table is also not moving. So that means the resultant force on the table is 0. Okay. But this is not what we need to see. Okay. Anyway, let's look at this one first. Okay. So same size. Both are the same size because that's why it's in equilibrium. Then same line of action, you can see both of them pass through the same line. So same line of action, act in opposite directions. Can you see? But they don't act for the same time. Now if you remove this from the table, then there will be no more reaction force. But the weight force is still there because it's on the earth. So you see these don't act for the same time. So you can even check this one out. Okay, I will use another color. Okay, so you can see these 3 criteria are met. But these 2 and also this 6th criteria is not met. So therefore it's not a Newton's third law pair. So you can use the first 2 to identify whether it's a Newton's third law pair right away, because these others can still apply to them. Okay, even when it is not a Newton's third law pair. Any question?
Sir, but still Newton's third law applies there, right?
What do you mean?
So every action has an equal and opposite reaction.
Yes. Okay, so it's not, yeah, these 2 are not Newton's third law pair. Okay, now what you are asking is this. Okay, so where is the now you see every action has an equal and opposite reaction. That's what you are saying. It's correct. That is Newton's third law. So I will write that down. Okay, so Newton's third law states that for every action there is an equal and opposite reaction. For every action there is an equal and opposite reaction. Also we can say another way of saying this is if body A exerts a force on body B exerts an equal and oppositely directed force on body A. Okay, so another way of stating Newton's third law is if body A exerts a force on body B exerts an equal and oppositely directed force on body A. This is Newton's third law. Now, so what is the equal and opposite force for each of these forces? So what we will do here is, now I will show you what that is. Okay. So now if you consider this this book, there is a reaction force exerted by the table on the book. Okay. Yeah. So that means there should be an equal and oppositely directed reaction force exerted by the book on the table. That is this one. Okay. So what we can say is by Newton's third law. So the Newton's third law pair is this one. Okay. So what is, yeah, so we have the red R. I will write that red R. Sorry, the red R. I will use the color so that you can identify. Okay. So this R here, R is equal to this R here. by N3, Newton's third law. Do you get it? So the reaction force exerted by the table on the book is equal to the reaction force exerted by the book on the table by Newton's third law. That is the Newton's third law. Now you may be wondering, what about the weight? Okay, so I will try to draw it here. Okay, so let's say this is the earth. That is the earth, and let's say this book, that is the book. Okay, the book is on the table, that is the book. Now there is a weight force exerted by the earth on the book. We call that W. That is this W. Okay, maybe I can use the same brown color so that it's easy for you to understand. Okay, so we have this W. Okay, that is the weight of the book. So now there should be, Newton's third law says that there should be an equal and opposite force for every action. There is an equal and opposite reaction. So the equal and opposite reaction is the weight force exerted by the book on the earth. So that is that one. Do you get it? Okay, so the book also exerts an equal and oppositely directed weight force on the earth. But the earth doesn't move towards the book. Rather, the book moves towards the earth because the earth is gigantic, massive compared to the book. So the lighter object will move towards the heavier one. Okay. Now, same thing here also. Now, if you have two objects, any two objects that have mass will exert gravitational forces on each other. Okay. So then we can say W equals W by Newton's third law. The weight force exerted by the earth on the book is equal to the weight force exerted by the book on the earth by Newton's third law. That is the Newton's third law pair. N3, Newton's third law. Okay, but you can't say R is equal to W by Newton's third law. R is equal to W by Newton's first law. Okay, this is R. Okay, so for this one we can write R, I'll write it here, R equals W by Newton's first law. Or also we can say in terms of Newton's second law also. Okay, if you want by N2 also we can explain why it is equal. Okay, so if you say by Newton's first law, you can see it is stationary. It is in equilibrium. It is in equilibrium, the book. Okay, the book is in equilibrium because the resultant force on the book is 0. Okay, so this is for the book. For book. Okay. So by Newton's first law, which states that if the object is stationary, it will continue to be stationary like that unless acted upon by an external force. So no external force here. These forces are balanced, so it's stationary. Also, we can say by Newton's second law, no acceleration, no resultant force, so it has to be stationary. Any questions?
No.
Okay, so these criteria are very important. Okay, you should study them.